Imagine a cat sealed inside a box. This is no ordinary cat and this is no ordinary box. Inside this box, along with our feline friend, lies a device with a 50% chance of releasing a deadly poison. The catch? Until we open the box, the cat exists in a bizarre state, both alive and dead at the same time. This is Schrödinger's cat, a thought experiment devised by physicist Erwin Schrödinger in 1935. Schrödinger's cat isn't meant to be taken literally. It's an illustration, a way to grapple with the strange and counterintuitive world of quantum mechanics. In the quantum realm, the rules of classical physics, the physics of our everyday experience, break down. Particles don't exist in one definite state or another. They exist in a haze of probabilities, a superposition of states. The act of observation, of opening the box, forces the quantum system to choose a state, collapsing the superposition. Schrödinger's cat highlights a fundamental paradox in quantum mechanics, the disconnect between the microscopic and macroscopic worlds. In the quantum world, particles exist in a superposition of states. But in our large-scale world, we don't observe objects existing in two states simultaneously. How does the quantum world, with its blurry uncertainties, give rise to the concrete reality we experience? This question has plagued physicists for decades. Schrödinger's thought experiment, while absurd on the surface, forces us to confront the fundamental mystery of quantum measurement. How does the act of observation, a seemingly passive act, influence the state of a quantum system? The answer, it seems, lies in the delicate and fragile nature of quantum states. Quantum states are notoriously fickle. They are easily disturbed by their surroundings, like a whisper lost in a noisy room. Heat, in particular, is a major culprit. Heat, in the quantum world, is essentially random motion at the atomic and subatomic level. This chaotic dance of particles disrupts the delicate coherence of quantum states, causing them to decohere and lose their quantum properties. Imagine a perfectly still pond. A pebble dropped into the water creates ripples that spread outward in an orderly fashion. This is akin to a coherent quantum state. Now imagine that same pond, but this time the surface is bombarded by raindrops. The ripples, instead of spreading out in an organized manner, are quickly disrupted, their pattern lost in the chaos. This is what heat does to quantum states. For decades, scientists believed that quantum coherence, that essential quantumness, could only be maintained at extremely low temperatures, close to absolute zero. At these frigid temperatures, atomic motion slows to a crawl, minimizing the disruptive effects of heat. However, recent breakthroughs have challenged this long-held assumption. In a groundbreaking experiment, researchers at the Institute for Quantum Optics and Quantum Information in Vienna have demonstrated quantum phenomena at surprisingly high temperatures. This discovery has sent shockwaves through the scientific community. It opens up the possibility of harnessing the power of quantum mechanics in environments once thought impossible. But how did they do it? How did they coax these delicate quantum states to survive in the warmth? Section 5. The Vienna Experiment, Light and Levitated Nanoparticles. The Vienna experiment centered around a tiny glass sphere, just a few hundred nanometers in diameter, about the size of a small virus. This nanosphere was levitated inside a vacuum chamber using lasers. Think of it like a tiny ball suspended mid-air by beams of light. The researchers then used another laser to carefully nudge the nanosphere, causing it to vibrate. Here's where the quantum magic comes in. The vibrating nanosphere wasn't just vibrating in any old way, it was vibrating in a superposition of states, essentially occupying two different vibrational states simultaneously. And here's the kicker. They managed to maintain this superposition at temperatures much higher than anyone thought possible. Section 6. Maintaining coherence. Trapping light in a tiny cage. The key to their success lies in the way they trapped the nanosphere. By levitating it within a highly focused laser beam, the researchers created what's known as an optical trap. This trap acted like a tiny cage for the nanosphere, isolating it from its surroundings and minimizing the disruptive effects of heat. Think of it like this. Imagine a delicate soap bubble floating in a windstorm. The wind, like heat, would quickly tear the bubble apart. But if you could somehow enclose that bubble within a protective sphere, shielding it from the wind's chaotic force, it could remain intact. That's essentially what the optical trap achieved for the nanosphere. Section 7. A quantum leap implications for technology. The implications of this discovery are far-reaching. If we can maintain quantum coherence at higher temperatures, it opens up a world of possibilities for quantum technology. Quantum computers, with their unparalleled processing power, could become more practical for real-world applications. Quantum sensors, capable of detecting minute changes in their environment, could revolutionize fields like medicine and materials science. Imagine a quantum computer operating not in a specialized lab cooled to near absolute zero, but in a regular server room. Imagine quantum sensors implanted in the human body, monitoring our health with unprecedented precision. The Vienna experiment suggests that these futuristic scenarios might not be so far-fetched after all. Section 8. Reality Redefined. A philosophical perspective. Beyond the technological implications, this discovery also forces us to confront profound philosophical questions about the nature of reality. If quantum phenomena, once thought to be confined to the microscopic world, can persist at higher temperatures, what does this say about the nature of our macroscopic reality? Is the world we experience, a world governed by the familiar laws of classical physics, merely an illusion, a veneer over a deeper quantum reality? These are questions that philosophers and physicists have grappled with for centuries. The Vienna experiment, by blurring the lines between the quantum and classical worlds, adds a new layer of intrigue to this ongoing debate. Section 9. Conclusion. A universe of possibilities. The discovery of quantum phenomena surviving at higher temperatures is a testament to the power of human ingenuity and our relentless pursuit of understanding the universe. It shatters our preconceived notions about the fragility of quantum states and opens up a universe of possibilities for future technology and scientific exploration. As we delve deeper into the quantum realm, we are likely to uncover even more surprises, challenging our understanding of reality and pushing the boundaries of what we thought was possible. The journey into the quantum realm has just begun, and the future, it seems, is filled with quantum possibilities.